Right. So my name is Zach Shberek-Conti, and I'm a research associate at the Alan Turing Institute in London. And for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. So on a side note, if you're interested also to share your work within this remit in one of our upcoming seminars, please feel free to get in touch with us. And as for the format of the seminar, our speaker today will talk for around 40 to 45 minutes, followed by a Q&A session as is normal. And you may ask your questions in the chat box or you even may ask in person. So without further ado, I'd like to introduce our Dr. Ricardo Vinuesa, who is our speaker for today. Dr. Vinuesa is an associate professor at the Department of Engineering Mechanics at KTH, Royal Institute of Technology in Stockholm. He is also a researcher at the KTH Climate Action Center and vice director of the KTH Digitalization Platform. He studied mechanical engineering at the Polytechnic University of Valencia, and he's received his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. His research combines numerical simulations and data-driven methods to understand and model complex wall-bounded turbulent flows, such as the boundary layers developing around wings and urban environments. Dr. Vinuesa has received, among others, an ERC Consolidator grant and the Goran Gustafsson Award for Young Researchers. So with that, I thank you all for listening and welcome Dr. Vinuesa to take the floor. Thank you.
Thank you very much for the kind introduction and for the invitation to deliver a seminar in this very nice context. I'm going to talk to you today about modeling and controlling turbulent flows through deep learning. So I would like to start by motivating a bit this work through this slide from Airbus. If one looks at a typical airliner, then around 50% of the total drag comes from friction on the different surfaces of the airplane. Around 40% comes from the lift-induced component, which happens at the tips of the wings, and that's about 90% of the total drag. So the dominant contributions. Try to understand how one can develop more efficient aircraft. And if one focuses on the friction drag, around 50% of it comes from the wings. So analyzing the wings of an airplane really helps us to try to develop more efficient solutions in terms of aerodynamic performance, but also hopefully having lower emissions and a reduced economical cost of operation. So these are challenging fluid mechanics problems for which we use a number of methods. We use high fidelity numerical simulations. We use the spectral element code NEC 5000 developed by Fisher and others, where what we do is that we combine the geometrical flexibility of finite elements with the high order convergence of spectral methods, and in such a way that we can obtain, as you can see here at the bottom right, a little video of the type of simulations that we can do. So we can simulate with very high level of detail up to the smallest vertical structures, configurations in quite some complicated geometries like wings. And so this is the type of behavior that we're going to be discussing today. And basically, we can use this high fidelity approach to perform simulations on a wide range of conditions. Here I'm showing you turbulent wings at Reynolds numbers ranging from 100,000 all the way up to 1 million. And the million is an important case because it already has important implications for the aerodynamics of a full-scale aircraft. All this data can be found in this reference, Vinuesa and others, in the International Journal of Heat and Fluid Flow, 2018. And this wealth of data is what allows us to train, well, basically more robust and more general data-driven models, as I will be talking about in a second. One limitation of these simulations that I have been discussing so far is that when we try to increase the Reynolds number and we try to go to more extreme conditions, then we end up with this aspect ratio of the elements close to the far field, which limits, in terms of the pressure iterations, our performance. That's why it's beneficial to use the adaptive mesh refinement strategy. So as you can see here, one can perform adaptive meshing. So the mesh is automatically refined close to the wing. We can have coarser meshes farther away from the wing, and you can see the stringwise evolution of the wingtip vortex. This is a wing that has it's a finite wing. So you have a rounded wingtip where this vortex can roll up and produce the effect of the lift-induced drag. And this is very important because this 40% of the total drag comes from these vortices, and this very, very detailed data can actually be used to understand the physics and to try to train important models. This is work by Siavash Toshi, who will be presenting this in the LES conference. And I want to show you a short video illustrating a little bit of the phenomena that we can actually achieve here. So, as I was showing before, here we have this turbulent wing, we have the wake. At the wing tip, we have this wing tip vortex that is forming and rolling up around the wake. We have an important effect, and is that essentially what the wing tip is doing, the wing tip vortex, is that it's introducing a rotation which is pulling down the wake, and through this pulling down, it's affecting the capacity of the wing to extract lift. So it's essentially reducing the effective angle of attack, which means that to achieve the same lift, you need to increase the angle of attack, leading to increased drag. And that's the main effect of this wing tip vortex. And you can see the very high level of detail that we can obtain with our simulations. These are high fidelity simulations, essentially a bit of a coarser DNS. You can see the wing tip vortex here, and you can observe the effect of the rotation that is produced by this vortex. The reason why I'm showing you these visualizations and all this richness of physics is that we can exploit all this information to be able to harness the potential of deep learning methods to be able to to control, to get some modeling ideas, and also to establish some physical phenomena that are relevant in this context. Here you can see a close-up view of how the vortex is rolling up and is producing this vertical motion, again, leading to the effect not only on the turbulent boundary layers, but also on the wake. In fact, you produce some local relaminarization because of the strong acceleration that is being introduced by this vortex. So you see that we really have quite some detail in our simulations. These are basically cases that require terabytes of data to be able to store all of this information. This is around 1 billion grid points in terms of mesh resolution. So these are very large cases from which one can actually benefit in terms of data analysis. Okay. So this is from the fluid mechanics point of view. It turns out that the usage of machine learning for fluid mechanics has quite some range of applications. 20 years ago, Milano and Komosakos introduced the usage of deep learning to model the near wall region of a turbulent channel. More recently, there has been work on SES modeling, introduction of inflow and boundary conditions, RANS modeling, capacity of enhancing some measurements with physics-informed neural networks, and also possibilities for flow control. So in the end, there are many areas where machine learning can be applied and has been applied already in many of these contexts. We are currently exploring different directions. Here is a review paper together with Steve Branton published in Nature Computational Science. You can see the whole reference here at the bottom, where we explore and document the potential of machine learning in the context of CFD, of computational fluid dynamics. So essentially what we document is that there is quite some possibilities from machine learning to accelerate DNS, direct numerical simulations, to improve the modeling, both in the context of LES and RANS, and to develop more robust reduced order models. That's this last section over here, which I will be talking about today in some examples. So just to clarify, we don't claim that machine learning can replace any of the strategies for CFD, but it can help and it can complement some of the methods within CFD to be able to obtain more consistent and robust results. Okay. So what I will be doing now is that I will tell you some examples of application of machine learning to fluid mechanics that we have been working on. And we're going to start with non-intrusive sensing. In non-intrusive sensing, what we do is that we consider, we consider a turbulent channel, for example. We consider measurements at the wall, and from those measurements at the wall, we're going to predict what happens to the flow above the wall. We do that because that will enable us to perform better flow control strategies. If we know what the flow is doing, we can control it better. And it's much easier to measure at the wall than to measure at the flow location, where you are actually disrupting the fluctuations there. So we will use 3 quantities at the wall, the 2 wall shear stress components and the wall pressure, and we'll predict the 3 velocity fluctuations at a particular wall normal location. To do that, we will use different deep learning methods. For example, convolutional neural networks. All these results, by the way, are summarized in this article that you see at the bottom. Guastoni and others, he's a PhD student in my group. We published in the Journal of Fluid Mechanics, and all the details are provided there. We first performed 2 direct numerical simulations of a turbulent open channel at friction Reynolds numbers of 180 and 550. The domains are large enough, and this data will be used to establish a mapping between the wall information and the information above the wall. Because we have images and we have quite some spatial information in this turbulent flow data, it's more convenient to use convolutional neural networks than to use fully connected networks. The fully connected network that we're showing over here is characterized by having all the neurons of one layer connected with the neurons of the next layers. In this sense, we are losing the possibility of exploiting the spatial information in the data. With a convolutional neural network, what we do is that we have this little kernel that you see here, this little window, which is sweeping through the input. And what this does is that it's performing a convolution operation in such a way that one point in the output receives information from 9 points in the input, and it's taking advantage of the spatial distribution of those points. So we can effectively apply computer vision strategies and exploit some of this spatial information in the data, in the flow. So this is one of the architectures that we consider. This is a CNN, a convolutional neural network with 6 hidden layers. We have 3 input planes, which are the 2 wall shear stress components and the wall pressure. We have 3 output planes, which are the 3 velocity fluctuations at the desired wall normal location. And in each of the hidden layers, we have a number of filters that is indicated by these numbers over here. So essentially, what we are seeing is that the filters in the first layers are identifying more abstract features in the data, like rounded regions, edges, recirculations. And as we are going deeper into the network, we are hierarchically building more complex features. And those features are basically the turbulent extractors that we want to predict. So the neural network is learning in a hierarchical manner from more abstract to more and more elaborated features, which is in a way how turbulence works. Turbulence is also hierarchical, and this hierarchy of scales is what allows us to establish phenomena across all these interscale methods that one can try to get into turbulence. So the way in which the neural network is training and is being performing the predictions is the way in which you are actually turbulence is working, not physically. So doing things like that, one also realizes that the first layers are looking at smaller objects and the last layers are focusing on larger features in the data. So this is the schematic representation, the 3 inputs on the left, the 3 outputs on the right. We actually apply some padding for periodicity, and we train our network to perform these predictions. What I have shown you so far is what we call the FCN method, fully convolutional network, but one can also perform a proper orthogonal decomposition, which that's how we call PCA in fluid mechanics. And then we can basically decompose the spatiotemporal problem into spatial modes and temporal coefficients in such a way that we only need to predict the temporal coefficients of the signal. So doing things like this, well, we can, in principle, simplify the prediction problem. We need to predict the whole signal, just the temporal coefficients, and try to see what the performance would look like in this scenario. So what I'm showing you here is the instantaneous streamwise velocity fluctuations. The third row would be the DNS, that's the reference. The first column is y plus 15, that's a plane close to the wall. The second column is y plus 100, that's in the outer region. These all results at arita of 550, so that's the higher Reynolds number. And the first row is extended POD, so it's a prediction based on a method that is formally equivalent to linear stochastic estimation. So in this approach, what we realize is that because turbulence is non-linear, the linear method is only able to capture part of those interactions, but not the non-linear ones. This leads to streaks being significantly attenuated in terms of the level of the fluctuations and also filtered out. You can see that the signals are much smoother in the case of the extended POD than in the reference. Therefore, there will be much more deviation than with non-linear methods. The neural networks, of course, because of the nonlinear activation functions, are able to reproduce some of these nonlinearities. In the last row, we see the FCN, the fully convolutional network, where we are predicting the whole signal directly. And we see that close to the wall, the agreement is very good. So we can actually obtain a very, very good prediction of the flow close to the wall based on the FCN. Farther away from the wall, if we look at the FCN POD, which is the second row, remember that in FCN POD, we only predict the temporal coefficients, then we see that the agreement with the outer region is actually quite good. It's not as good as what we observed before close to the wall for the FCN, but certainly the FCN POD is able to encapsulate the dynamics of these larger scales into few POD modes, which can then be effectively predicted in terms of the temporal coefficients. So close to the wall, the FCN method is better. Far away from the wall is the FCN POD, which is actually better. We can look at this also from a statistical point of view. What I'm showing you is the stringwise, wall normal, and spanwise fluctuations. The black line is the reference, is the DNS. The triangles are the FCN. The blue dots are the FCN POD, and the squares are the linear method, that's the extended POD. And what we can see, first of all, close to the wall, the near wall peak FCN basically nails the near wall peak. We have less than 1% error, which is a very remarkable result because when you're doing flow control, in many cases, what you want to control is the near wall fluctuations. So if we can predict those very well, we can probably establish a very, very good flow control there. Now, if we look at the FCN POD, it actually outperforms the FCN statistically also at weight plus 100, which is pretty good. And the linear method, which are these squares, are underperforming in comparison with the nonlinear methods, again, due to the impossibility of reproducing the nonlinear interactions present in our flow. Okay? So everything that we documented instantaneously is also observed when we look at the flow from a statistical point of view. Something that I believe is quite interesting is the method of transfer learning. So basically, whatever we learn in one configuration, we can try to use it for another task that is similar to the original one, but a bit different. And this is something that we can observe in this first example. We can use a network train for the behavior close to the wall, and then we can transfer those weights to predict farther away from the wall. What happens is that we will freeze the 3 first layers, and we will only retrain the 3 last layers. That's because the 3 first layers are going to look at smaller, more abstract elements, which are going to be similar, close and farther away from the wall. And the last layers are going to be focusing on larger structures, which clearly are going to be more dependent on the wall normal location. So doing things like this and performing the transfer learning, what we see is that our new network has the same accuracy as the old one, but we have only 23% of the computational cost. So we can significantly reduce the cost in terms of computer time, but also training data. And another example, which I think is even more remarkable of transfer learning, is to transfer from low to high Reynolds numbers. So what we can do is that we can take a network trained at 180, a Reynolds star 180, take those weights and take them to a network, train at 550. And what we can do is to continue training beyond that point. Now, instead of randomly initializing the weights or using some algorithm of initialization, we just exploit the information that we knew at 180, and we keep training from there. And our results also indicate that the accuracy is the same, and we can use only 1/4 of the training data, which is remarkable because the data at higher Reynolds numbers is much more expensive to produce than the data at 180, which means that this is really a very, very promising venue to train neural networks for progressively more and more complicated and costly tasks. Okay? So this is, and again, all the details of this are in this JFM article in this Journal of Fluid Mechanics, so you can see all the details there. Now, another example has to do also with non-intrusive sensing, but in the case where we don't have full resolution at the wall, we just have a few point measurements here and there. To do this prediction, we're going to perform a task of super resolution because we want to increase the resolution of the information at the wall. And to do this, we're going to use another architecture, which is called GANs, generative adversarial networks. This architecture, which is shown over here, combines 2 networks, one generator, which is producing high resolution data from low resolution data, fulfilling the statistical properties of the reference data set, and a second network, which is called the discriminator, and is targeting being able to differentiate whether a particular image is real or it has been produced by the generator. So these two networks are trained together using game theory. So they both progressively get much better at their own tasks. And eventually what we obtain is a generator that is very good in producing realistic flow data. So we use this, as we see here, to obtain a two-step architecture. One step where we use low-resolution data at the wall to predict high-resolution data at the wall. And then using this, we will predict high-resolution data farther away from the wall. And the results of this are quite encouraging. Here at the bottom, I'm showing you the instantaneous wall shear stress. So we are having data at the wall. The DNS is here. On the top row, I'm showing you progressively more and more levels of downsampling, whereas this one over here has a downsampling factor of 16 squared, so very, very pronounced downsampling. And at the bottom row, I'm showing you the predictions. So we can actually see how clearly when I downsample more, the structures become attenuated. But the important thing is that the structures look very realistic and they have the right size, the right spacing, and the right locations. So one can actually use quite well these architectures to predict the flow and at least know where the structures are in case that we want to predict and perform flow control. Now, these results are summarized in this work by Güemes and others, published in Physics of Fluids also last year in 2021. If now we look at data far away from the wall, what we see is we are showing you the following columns. The first one is y plus 15, then 30, 50, and 100. So I'm moving farther away from the wall. And the rows, the first one is the DNS, that's the reference. As I move down, I'm showing you progressively more and more downsampling. So the easiest comparison is this one, which I'm comparing with this panel, because I am doing the prediction that is closest to the wall with the smallest downsampling. And the agreement, as you can see again, is really excellent. Of course, as I move farther away from the wall, the correlation between input and output data decreases. And if I increase the downsampling factor, I get less information from the input, which means that the prediction is going to get more and more challenging. This is what happens when I look at the bottom right panel, which I want to compare with the bottom top panel, and I see a significant attenuation of the structures. But still, I can locate the locus of the large scales of these large streaks and their spacing, their sizes. So if I want to do large scale control, at least I will know which are the structures that I want to target and which are the scales that one needs to work with in order to perform these flow control strategies. Okay. Now, I've shown you two examples of non-intrusive sensing, where I go from data at the wall to data above the wall. But what about the opposite task of using data from outside, from far away from the wall, to predict what happens close to the wall? This is an interesting task in the context of development of wall models, so that we can impose some boundary condition close to the wall, and that way we can save the computational cost of the very expensive resolution close to the wall. This is work that we have published in arXiv, so you can see the details here in the top right. Basically, what we observe is that this is a quite challenging task. It's more challenging to predict from far away from far away from the wall to closer to the wall than to do the opposite. Because when you're far away from the wall, your input does not have the small scale information that you need to predict. So you have less rich input data. And also your receptive field with respect to the size of those very large scales is actually much smaller. So you cannot so easily exploit whatever information you have in your input. In any case, what we consider is the overlap region at arita of 550. The columns are the U, V, and W fluctuations. The first row is at y plus 100, so far away from the wall. The second row is at y plus 50, so closer to the wall. Again, both of them are in the overlap layer, which means that they fulfill the same physical properties. And I want to develop a model to predict the plane at y plus 50. That's the one that I want to replace with a neural network. And that's the prediction that I have at the bottom row. So what we see is that the stringwise velocity fluctuations are very good. They're in very good agreement. The V and W show some of the most prominent patterns, but you can observe that there is quite some deviation in some of the structural patterns there. No? It's not so easy to make these predictions because of the two limitations that I showed before. In fact, if one looks at the power spectral densities, where the orange lines are the predictions, we can see that there is some deviation in the small scales, which is expected, and at the large scales also see a little bit of distinction with respect to the reference. Now, the problems of this prediction could be solved by using maybe a GANs that could reconstruct the missing small scales, and by playing with the max pooling at the input so that we can reorganize the input data in such a way that we can more effectively exploit the input information. Having said this, we still get 19% error in U, which is actually pretty good. And even if we would get a perfect prediction of the flow close to the wall, this doesn't guarantee us that this will be an adequate boundary condition. So there are other strategies, other possibilities that are being explored in order to be able to assess such a boundary condition strategy. Okay? But as a prediction exercise, I think that this is helpful and is valuable. Now, one more example has to do with reduced order modeling, which was one of the topics that I touched upon at the beginning when I mentioned our review paper. And of course, in this direction, a very well-known strategy is POD, proper orthogonal decomposition, or PCA, principal component analysis. In practice, they're essentially the same. POD has two important properties. One is the orthogonality. The modes are orthogonal in space, which this is a quality that actually helps a lot with interpretability of the reduced order model, and the optimality in a linear sense. And so each additional mode has less and less contribution towards the reconstruction of the signal. Now, what we want to do, and this is work by Vinuesa, Vassi, and others here published in Expert Systems with Applications in 2022. What we want to do is to use autoencoders to obtain a non-linear reduced order model of the original system, which hopefully will be more compact than the original POD strategies. The data that we use is this simplified urban environment that you can see. So using the same numerical strategy that I mentioned before, we can obtain a very, very high level of detail in the flow structures between the two obstacles. So we actually can see quite well the data that we can use. And we're going to predict the horizontal plane at middle way between the height of the obstacles. So we want to really look at the 2D horizontal plane. We use 1,200 snapshots to train the various reduced order model approaches. Now, what is an autoencoder? Well, here we use what we call a convolutional autoencoder because, as I mentioned before, the turbulent structures in the flow can be more effectively exploited by using convolutions, by using CNNs. Now, in an autoencoder, what I want to do is to apply a sequence of convolutions in this case, such that we can reduce the size of the input. So you can see that the size of this data is actually getting smaller and smaller until we reach this bottleneck at the middle. This is what we call the latent space, where we will have a compressed representation of the original data. And then we can upsample the data again to recover the original signal. So the autoencoder has a loss function where what we want is to maximize the reconstruction accuracy of the original signal, while at the same time being able to compress very effectively the data. Okay, that's a little bit the idea. Now, the autoencoder doesn't have any of the interesting properties from before. It's not orthogonal, neither can be ordered in terms of the contribution of the modes to the reconstruction. But there is the approach based on hierarchical autoencoders developed by Fukami and others, where what they did was to start with a first autoencoder, which has a latent space of 1, a dimension of the latent space of 1. This gives us our first latent vector. Then they have another autoencoder where the latent space has a dimension of 2, and we fix the first latent vector from before, so we get a new latent vector R2, which will have a smaller contribution towards the reconstruction of the signal. And if we do this recursively, what we do is that we end up with a list of latent variables which have less and less contribution towards the reconstruction of my signal. So I'm still not having orthogonal modes, but at least my modes can be sorted in terms of their contribution to the reconstruction. For orthogonality, we're going to use beta variational autoencoders, which allow us to introduce stochasticity in the latent space. So we're going to start by defining P of X as the distribution of the original data, P of R as a distribution of the data in the latent space. And the goal is to maximize this equation, which is the marginal likelihood. The marginal likelihood is the approximation of P of X with the parameters theta. We have a probabilistic decoder, which takes us from the latent to the original space, and a probabilistic encoder, which takes us from the original to the latent space. And the decoder is a generative model because we can take samples from our latent space to produce data in the original space. Now, turns out that the encoder has a Gaussian distribution with a particular mean and standard deviation. And we can sample this function by using random noise, which also follows a normal distribution. So our latent vectors are characterized by a mean, a standard deviation, and this random noise that we are introducing. Okay. Turns out that the loss function for the beta variational autoencoder can be defined like this. So we have one term which corresponds to the basically to the reconstruction loss, so being able to reconstruct the original signal, and the other term of our loss has this beta hyperparameter. Is basically a penalization. It's a regularization of the loss function, which is targeting at learning disentangle latent variables. And this is important because in principle, if I'm able to learn that disentangled representation in the latent space, I can probably be able to have a set of orthogonal modes, and I can also learn a parsimonious representation in the latent space. So the goal is to learn in the latent space a parsimonious representation, which is also disentangled. Of course, this requires adjusting the value of beta, of this hyperparameter, which will have an impact on the training and on the results, but that gives us in turn more flexibility in terms of the model that we're trying to learn. Okay. So this is the decoder on the top. We go from the latent to the original space, the encoder at the bottom, which takes us from the original to the latent space. And here I'm showing both the mean, the standard deviation, and the random noise that is being added in the latent space. Now, some results. Here I'm showing you the stringwise velocity fluctuations at the horizontal plane. Red and green denote high and low speed velocities, so positive and negative fluctuations. And here in the bottom right corner, I'm showing you the reconstruction from 5 POD modes. Now, this reconstruction is only 32% of the energy. So POD is not so good at being able to encapsulate effectively the information in the original system. And the 3 autoencoder-based approaches are all around 90% of the energy being reconstructed with only 5 modes. In fact, if we look at the details here on the right, we can see that this structure that you can see between the 2 obstacles can only be reconstructed by the autoencoder-based approaches, whereas the POD doesn't really highlight any of these features in detail that can be observed between these 2 obstacles. Okay, so what we observe is that the POD is not so good at compressing very effectively the data. You need on the order of several hundred POD modes to be able to reconstruct a significant fraction of energy in our field, whereas the autoencoders are very good at compressing, and with very few modes allow us to really reconstruct significant fractions of the original signal. Okay. Now, we can also look at the cross-correlation matrix among the modes to look at their orthogonality. So the POD clearly has 100% orthogonality. That's by design, it's this linear operator. The beta variational autoencoder has over 99% orthogonality, which means that the modes are orthogonal in space. This is good from the perspective of interpretability, because a particular physical phenomenon will be related to one mode and not a set of modes. No? So in principle, the reduced order model that we obtain from the variational autoencoder will be more interpretable. If we look at the 2 other autoencoder-based approaches here on the left, we see that the orthogonality is around 87%. So the modes are not really, well, they're not orthogonal, right? And they're not so easy to interpret in practice, no, in reality. this has an important implication from the perspective of the hyperparameter beta, which has a role in this loss function. So as you can see on the right, if I increase the hyperparameter beta, this blue line decreases. The blue line is the percentage of energy, of turbulent kinetic energy reconstructed in the original signal. What we see is that if I'm increasing the value of beta, my reconstruction will not be as good. But in turn, I'm going to increase this red line, which is the determinant of the cross-correlation matrix. So a large value of beta will give me more orthogonal modes with a slightly worse reconstruction and also a more sparse latent space, because we only have 3 non-zero variables in the latent space for the largest value of beta. If I start to decrease the value of beta, what I get is a larger number of non-zero variables, and what I have is a better reconstruction, but very bad properties in terms of the orthogonality. So this is the trade-off that we have when we're trying to play a little bit with the parameters of this beta variational autoencoder. So let's look at a comparison between POD and all the autoencoder-based approaches. Here on the right, what I'm showing you is the first 5 modes. The second column shows me the POD modes, which are the proper orthogonal decomposition. And here it's important to highlight that when you're looking at the flow between these 2 obstacles, there is a separation of the flow being induced, because of the sharp corners of these buildings. The POD modes are able to very nicely capture the behavior of this separation. And so we actually can see these high and low speed regions here, which are very, very closely connected with this separation. If we look on the right, where we have these 2 other columns, these are the CNN autoencoder and the hierarchical autoencoder. What we see is that these modes basically show some noise, some high and low frequency noise, but not really any spatial patterns that can be connected with any physical phenomena. And that's interesting because these approaches, these autoencoders, are very good at compressing the data, but a bit in an indiscriminated way. What we want to do with the beta variational autoencoder, which is the most in the first column, is that we observe quite some resemblance with respect to the POD modes. So we actually see that the first autoencoder mode also has this high and low frequency on the sides associated with the shedding. And in a way, there are quite some similarities between this autoencoder and these POD modes. The difference is that the autoencoder modes contain, in addition to the base physical phenomenon, the higher frequency turbulent fluctuations superimposed on them. So instead of having hundreds of modes to try to reconstruct those higher order fluctuations, the autoencoder encapsulates into these modes also the higher order fluctuations. So we have the main physical phenomena, we have an interpretable reduced order model, and at the same time, we also have the turbulent fluctuations which are coming together with it. I want to highlight that to obtain these modes in physical space, what we do is that we go to the latent space, we take one latent variable and make the rest equal to 0, and we decode that one. So that way we can go from the latent space to the physical one. And then we do things recursively like that in such a way that we can reconstruct in physical space those modes from the latent variables. There is also an algorithm that you can see here on the left to be able to take the beta variational autoencoder modes and sort them by energy contribution. You basically perform nested reconstructions of the data, and then you choose the combinations that gives us the best reconstruction of the flow fields. So in this way, using the beta variational autoencoder, what we have is orthogonal modes, which are as well ordered in terms of their contribution to the reconstruction, so it's easier to truncate. And also we have a very interesting property, and it's that they are nonlinear in terms of the reconstruction. So we can obtain this nonlinear reconstruction with orthogonality and some sort of optimality, if you wish, in the sense of that sequence of modes. And with the property of being able to significantly compress the system much, much better than the POD modes. So with very few, a handful of modes, you can actually get a significant fraction of the original energy. So I believe that there is quite some potential in being able to use these techniques, these autoencoder-based techniques, for reduced order models in turbulence, in high dimensional data, while retaining the physical properties that allow us to provide some more interpretability in our results. What is important here? These reduced order models are used in tasks that require a reduced computational cost. So you have the original system, which is quite expensive computationally, but if you want to optimize or design the flow control in a particular setting, well, it's going to be much cheaper to run the reduced order model than to run the full scale simulation. Of course, if the reduced order model contains the physical essential ingredients of the original data, then this will be a quite helpful framework for optimization at a reduced computational cost. And in this sense, the interpretability of the autoencoder models are very promising in terms of having a quite useful reduced order model for these tasks. Okay, so again, this work is published in 2022 in Expert Systems with Applications. The main author is Hamid Reza Eibasi. Okay, and now we're coming to the last example that I wanted to talk about today, and it's flow control with deep reinforcement learning, which is another area that is receiving quite some attention from many different areas, from many different perspectives and angles. Essentially, in deep reinforcement learning, or in reinforcement learning in general, what we have is an agent, which is our neural network, and an environment. And the environment in our context is the computational fluid dynamics code. So the CFD code where we are simulating our flow configuration. Now, the agent interacts with the environment through actions. And the environment has a certain state that evolves with time. And the environment also returns to the agent with a reward. And the reward is a measure of the quality of those actions under a certain norm. And so depending on what we want to do, we may define a reward or another one. Again, this is just a measure of the quality of those actions. So of course, when we are changing our actions, we are making the system evolve in a particular way, changing its state and changing the rewards. What we want to do is maximize the reward. And to do that, we want to learn a policy pi, which gives us the optimal actions given the state of the system, such that we can maximize the expectation of the reward. So of course, we are working statistically in this framework. We have an expectation of the reward in the future. And then what we want to do is basically have a set of actions that give us the best reward, the maximum reward in the future under a certain time horizon. Okay, that's what we want to do with reinforcement learning. This again is work by Luca Bastoni. This was presented last year in the American Physics Society, and we are now preparing several articles on these results. So the first example that we look at is this two-dimensional channel. It's a very simple flow case, is 2D, where we impose suction and blowing at the top wall in such a way that we introduce a recirculation bubble at the bottom wall. And this recirculation bubble, this region of negative velocity, can be actuated through an actuation upstream of the bubble. So in this region, what typically can be done is to apply periodic forcing. So you try to do a stability analysis of the flow, you look at the most unstable frequencies, and then you have a periodic forcing with those frequencies, or with that frequency, the worst one, to try to act and reduce the length of the separation. Okay. What we will try to do with the DRL, with the deep reinforcement learning, is to discover more nuance, more detailed, and more tailored control strategies to these flow configurations. So this is the flow setup. The color region is the one of negative velocity. These dots over here are the probes where we're measuring the flow. This square is the region where we set up the actuation, and the actuation is modeled by this volume forcing, which is basically representing either suction or blowing. So we can either blow, flow, or suck it away from the domain. And we're looking at learning the optimal amplitude within this forcing to represent this, this actuation. In this arrow over here represents our reward, which is basically, as I mentioned, the length of the separation. Okay. So having set up the case, let's look at what the control looks like. This is the video that I'm showing you here at the left. What you're going to see when we set up the control is that we have wave packets that are sent with a particular frequency between these waves. And then at some point, this pulse stops. a while, there will be another pulse being sent from the actuation that you can see now. So you can see that the control has at least two frequencies, one that is connected with the separation between those wave packets in time, another one that is connected with the length of the separation bubble. So you can find a time scale related to that. So the control discovered by the DRL is more nuanced, more sophisticated than the periodic control, which has just one single frequency. Okay? And our results corroborate that. Fixing the control to a very small actuation, to a maximum amplitude of something like 10 to the -5, so really very small amplitude, what we can see is that the bubble reduction with the DRL is around 30%, whereas the periodic forcing gives us only 20% bubble reduction. So we are able to significantly outperform the classical technique, the classical method of periodic forcing, through a much more sophisticated control strategy that is learned by the DRL. Okay? And then some very recent results that we are very happy about are DRL to perform opposition control in a turbulent channel. So now it's not a 2D case, now it's really a three-dimensional turbulent channel. We consider first a minimal channel. So that's basically a channel of a small size where the physics is slightly simpler than a full channel. And what we observe is that the DRL used to perform blowing and suction, used to perform the control, leads to a drag reduction of 40%, whereas the classical control, which is something called opposition control, in which one is just trying to attenuate the fluctuations close to the wall, then one only obtains 30% of drag reduction. And that's what we can see with this evolution of the drag reduction as a function of time in the various strategies. So interestingly, also in these cases with turbulence, with higher dimensionality, with more complexity, one can use deep reinforcement learning to perform flow control. In fact, if we use the same policy that we learn in the minimal channel for a full channel, we still obtain these results where DRL is outperforming the opposition control. So these results are quite robust as well. And this is pretty much it in terms of my results. This is a summary of my conclusions. I use CNNs for computer vision applications, GANs for super resolution, autoencoders for modal decomposition, and deep reinforcement learning for flow control, which I believe has quite some potential. I also want to announce that I have several PhD and postdoc positions open in my lab. So if you're interested, please contact me. And here I'm showing you the various channels to contact me in terms of email, social media. If you have any questions, feel free to contact me, to discuss or to share ideas. For the moment, I would like to thank you very much for your attention, and I will take your questions.
Thank you very, very much, Ricardo. Thanks for the fantastic presentation. It was really well-rounded.
Thank you very much.
I'll open the floor for questions. I have a question, but I'll see if anyone has a question in the meantime. So, okay, I'll go ahead and ask. So with regards to the autoencoder reduced order modeling approach, obviously I instantly came to mind, methods like dynamic mode decomposition, and I noticed that in comparison with DMD, it seems from an autoencoder approach you are not able to extract things like eigenvalues, right?
No, exactly.
In relation to that, also, are you able to recover kind of the, let's say, dynamic operator from the latent space? Because like a DMD, the nice thing is that it gives you the unforced, the undecoupled state update, matrix, which is kind of quite critical in terms of when you want to capture the governing dynamics of a system.
No, that's an excellent question. From that perspective, DMD is better in the fact that you can get more physical intuition for those modes that one obtains. Here, what we are targeting is more compression. So being able to really have, with very few modes, most of the dominant dynamics. In that sense, of course, we outperform POD and we outperform DMD. When it comes to being able to use this as a dynamical system, there is some work to be done. All the temporal information is encapsulated in those latent variables, which have the space and time. and they're very difficult to interpret. I mean, you were asking about being able to understand the dynamical system. That's challenging. There is some work being done in this direction. We have also some ideas on how to expand that, and that's work in progress. At the moment, what we can do for sure is that we can, using the weights that we learn, the parameters that we learn, to really perform this for predictive tasks outside the training data set. And so we can actually use the autoencoder to advance the reduced order modeling time in other configurations that have not been seen in the training set. When it comes to even incorporating maybe physical constraints in the latent space, I think there is a lot of potential and there is a lot of nice things to be done, but it's a quite the emerging area of research, I think.
It is, yes. I myself am working kind of in a similar area, but focusing on energy and temperature prediction in buildings. But
if you're interested, we could collaborate and discuss a bit more. And
absolutely, yes.
Have a look at the paper, and we can of course discuss. Yeah,
I will indeed. I'd be happy to talk even in another session.
Yeah, absolutely.
In the meantime, I would again ask if there is any further questions. But it seems your presentation was very, very clear.
Looks like.
No, it genuinely was. Like I really enjoyed that. It was extremely well communicated.
Thank you very much. Thank you very much. I appreciate it, and I appreciate very much this invitation. This is an excellent venue and a great forum to share some of my ideas, and I'm very happy to get more questions afterwards, to discuss more, and to stay in touch. Brilliant.
It's our pleasure. We're really hoping to, we've grown a really nice community now. There's over 200 and almost 300 subscribers actually.
Wow.
And we're really trying to turn this into more of a platform. So hopefully we can, also use this as a platform for collaboration, not just with us, but also with internally within the community.
Absolutely, that sounds excellent.
Yes, and I can also say that we're trying to organize a conference on this topic, because it seems that there is no conference yet that focuses on physics-enhanced machine learning, particularly for engineering applications. And I think it could be really cool for people to come together. So but obviously we're assessing right now what the demand or what the potential of contributions would be. So
I think it sounds like an excellent idea. Actually, that's really good.
Yeah. So again, I'll be in touch even on this perhaps. All right.
Excellent.
I don't want to keep you take your time further, but I'm giving the last opportunity for a question. If not, I'll call this a day. And thank you once again for sharing your work.
Thank you very much.
Good day to everyone.
Bye bye.
Thanks, Ricardo. Bye bye. Bye all.